Okay, I hope everyone enjoyed Middle so far, and thanks for joining this MONAI meetup. So I'm talking about a federated learning technology and also how it's integrated with MONAI and how we're using it at NVIDIA. So first of all, what is federated learning, right? So you can think of it as a form of machine and deep learning on decentralized data. So this enables mostly devices that live on the edge to do state-of-the-art machine learning without a need to centralize the data and with privacy in mind. And one of the main assumptions, I think we also heard it in the previous talk, right, is that more data typically results in better and more generalizable models. So the motivation for federated learning really comes from these privacy concerns and regulatory restrictions that we have around personal data. This is especially important in the healthcare sector, right, where you're dealing with patient data. So private data can typically, or at least not easily, be shared across institutional boundaries. Anonymization is not always effective. Also, data custodians, data owners typically want to make sure they keep control of their data, especially if it's including annotations, right, which is costly to generate. So overall, bureaucracy of centralizing data is very complex. So federated learning kind of tries to get around that constraint by sharing models rather than the data, right? So we can, each of the data owners can keep control or governance of their data while they can still collaborate or make their data available to some entity that wants to train models on it. There are different flavors of these decentralized learning approaches. One would be this kind of cyclic idea. So it's like a continuous transfer learning. You send a model between institutions, or what is more commonly known in the federated learning space is the so-called federated averaging. So here, each model is training locally on their own data, or each site is training locally on their own data. And then we have a way to aggregate these models once in a while to achieve a better global model. On the communication architecture, also many different flavors. You could think of this client-server architecture where you have like a central hub where each data owner is communicating the model updates to aggregate, or we can have more direct or even more decentralized architectures that do a peer-to-peer communication. So here you don't have a central server even. And of course, you can think of hybrid architectures as well. One distinction I want to make is somewhat the healthcare versus mobile phone sector, where federated learning actually originally was proposed. In the mobile phone sector, you typically have these small devices, edge devices, as I said, which have typically low compute capabilities, low data, but you might have thousands or even millions of these, right, that are connecting to the server at different times, right? They might only be able to do training when they're plugged in. So you have a kind of a different population of data owners connecting to the server and contributing to the model training. In the healthcare scenario, we typically have this so-called cross-silo scenario where data owners might be an entire hospital or university or even a company, right, that have typically dedicated data centers with good hardware and stable internet connections. So the scenario is, from the design point of view, is slightly different. I'm not saying that the mobile phone sector is not useful in healthcare, right? You can think about this cross-device scenario being applied to medical devices, like wearable devices and things like that. So this is also very relevant. If you're interested in this topic, a couple of years ago, we published this paper in Nature Digital Medicine that goes into the impact of federated learning for different stakeholders in healthcare, going from the clinicians to patients, researchers, hospitals, and device manufacturers. Let's now, to get everyone on the same page, let's start with a very simple introduction of the federated averaging algorithm, which is kind of I would say the most common approach to do federated learning. In this way, the server is initializing a global model, right? This could be a pre-trained model. It's sending it to all the data owners, which have the compute on site, in this case, GPUs, right? They have the private data. So they train the models locally for some time and then send a weight update back to the server. So the server then does a weighted aggregation, typically based on the data sizes, could be other considerations, to update a global model and then send the model back to each data owner for continued training. So you can iterate this for many rounds, and then your model will converge. Here, of course, there's still some kind of consideration that this model updates might be leaking some sort of data about, like, information about the private data. So you have the option here to add additional privacy preservation techniques like differential privacy or encryption to make sure that no data is being leaked out. We've done this now a couple of times in the real world, like also on a global scale. A set of publications. I will not go into detail apart from the last one, but this one is actually quite interesting to illustrate the benefit of federated learning. So here we have a abdominal CT segmentation task for segmenting pancreas in contrast enhanced CT, and we have two clients. One client has only healthy pancreas cases, so in their labels they only have background and pancreas, while the other client has actually mostly cases with pancreatic tumors. So they have three classes: background, pancreas, and tumor. So now if we apply the model that is like a local model that's only trained on the client 2 data containing pancreatic tumors and apply it on a healthy CT scan, you can see that the model is actually tending towards predicting a false positive tumor here, right? Which is of course something you want to avoid. But if we use federated learning and we can basically jointly train on these 2 data sets, our global model performs more reasonable here and doesn't give a false positive segmentation. Similarly, if you think about the other way around, the model that's only locally trained on the healthy pancreas data, of course, has no concept of a tumor. So it will completely miss this tumor region in the deceased patient. While the global model at least does detect that there is a tumor, right? It's not exactly the same as the ground truth, but it does a reasonable job in highlighting this region. Okay, so the largest study I've personally been involved with, and it was mainly led by 20 different sites across the globe and NVIDIA. Was published in end of 2021, so we kind of started working on this pretty early on in the COVID pandemic, trying to estimate the oxygen treatment needs of patients arriving in the emergency department with symptoms of COVID-19. So the input to the model is actually an X-ray and then also some EHR data that includes blood tests and demographic data. And the model was basically extracting features from the X-ray and combining that with the EHR features to then predict the amount of treatment needed, going from room air, which is basically no treatment, to ventilator, and then also estimating the risk of death in a 24-hour and a 72-hour period. And as I said, this is a global collaboration. So we had sites across most of the continents, I could say. In total, 20 sites across 8 countries. Again, this is real world study, right? So you can really see diversity and the amount of data that different sites had. Also intensity profiles here of the X-ray shows the diversity of different scanner types. And so this is like showing real world domain shifts, which make it a bit more challenging to run these federated learning algorithms. And then also on the EHR data, we see how the patient populations are different, right? Typically, they are on the let's say the typical risk population for COVID-19, right? Having complications with the virus. But we also has like a pediatrics hospital included here, which we can see the patients are much younger. So again, where we can see the benefit of the federated learning is that we can see an improvement in the overall quality of the model compared to all sites if they train the model only locally on their own data by 16%. And then where you really see the benefit is the generalizability. So here we measured a 38% improvement in generalizability. And the way that the generalizability is measured is that we take all these locally trained models and test them on the other sites' testing sets, right? So it basically gives you an indication here on the x-axis, like how much data these local models had to train their model and how well they perform on the other clients' testing set on as measured by average AOC. So you can see, of course, data models with small amounts of data, they don't generalize well at all. But even the largest size doesn't do as well as the global model that basically benefited from virtually from all the data being available in the whole collaboration. And then we also evaluated this model on a set of on 3 data sets from different hospitals that were not part of the client's consortium that was used to train the federated learning model. And we can again see that the models generalize pretty well, especially for the need for predicting mechanical ventilation, which is, you know, one of the most key treatment decisions. They achieved a high sensitivity and specificity. Okay, so this is kind of to give you the background about the federated learning. And now, since the MONAI 1.0 version, we have a integration of federated learning concepts in the MONAI core. And the idea here is really that we can take models that are developed with MONAI, and typically these are models that are also being made available to the model zoo. So they're put into this MONAI bundle format, and we can upload these to the FL server, distributed to different clients, and there's an API, standardized API that allows them to run these models. They can also be used to customize your own implementations, and we'll provide a MONAI algo class that works with the MONAI bundles out of the box. So you can use models from the model zoo off the shelf and run them in federated learning scenarios. We do have a working group that's led by Jairashvi Kalpathy-Kramer, Daniel Rubin, and myself. We are mostly working on including more examples using different FL frameworks. There are actually several open source solutions available in the community. So we want to make sure that they all can support MONAI bundles and running MONAI developed models in federated learning scenarios. So we're building these reusable components, and a part of that is also the standardization. So if you're interested in contributing, we're always looking for input. There's a survey you can fill out, and you can reach out to me if you want to be included in the group meetings. We are meeting every 2 weeks at the moment. Okay, so now I'm kind of moving towards the demo, and to give you some background there, like I'm going to be using NVIDIA's federated learning solution, which is called NVIDIA Flare, which is really agnostic to the industry that you want to run your federated learning application. So healthcare and medical imaging is kind of only one aspect of that. But we of course, we work very closely with MONAI to make sure that everything that MONAI is developing is also supported by NVIDIA Flare. We try to cater to different personas, starting from federated learning researchers, data scientists, and platform developers. And it's kind of a growing set of features that NV Flare supports. We have a simulator for rapid development and debugging. We have some data statistics methods that allow you to analyze the data you want to train on. We are integrating with different training frameworks like XGBoost and MONAI. It's basically agnostic, right? We can run TensorFlow models, we can run TensorFlow models and PyTorch and other, or it could be just NumPy-based workflows or sklearn. And we have dashboards to allow you to operate a real-world system mostly using command line interfaces and an API that can allow you to automate some of these steps. And then security is a major interest or like a supported feature of NV Flare. It allows actually each client to set their own policies that allows them to really tailor the security requirements for their own site, for their data. There are several institutions and companies already using NVIDIA Flare, which I'm not going to go through. And to give you the basic or the main concept that Flare is making use of is this task-based execution of workflows in a distributed setting. So the workflow is implemented by a controller on the server. Basically allows it to assign tasks to individual clients. The clients then execute a task, send back a result, right? So in this way, you can implement this federated learning very easily. In the first step, the server is basically assigning the task train. It sends, as part of the data, it sends the global model. Clients continue training on the local data, send back the model updates to the server, and then the controller would be doing the averaging and the updating of the global model. And then, as indicated here, we can add additional filters very easily to these workflows that allow you to do customization of the data, conversion, or especially if you look at the results that are being sent back to the server, this could be including differential privacy or encryption. We've implemented quite a few baseline algorithms that are popular in the federated learning literature that you can try. And using the simulator, you can easily run experiments, say comparing centralized training versus federated averaging, HE here stands for homomorphic encryption, so that makes the computation more secure while keeping the same performance. Then we can analyze data heterogeneity. What happens if clients have very different label distributions? And this is the cipher 10 example. So it's a classification task. You can see as the heterogeneity goes up with a smaller alpha values, the performance of federated averaging decreases here. But then we can use some of the more advanced algorithms like Fed opt or scaffold. You can see that some performance is recovered here compared to the federated averaging. Again, this is showing the filtering concept. Filters can be implemented as part of these communication workflows, and they can be enforced by each of the clients by setting local privacy policies. And that's really relevant, as I said, for things like homomorphic encryption, where all the updates are being encrypted. The server does actually the aggregation in encrypted space and sends back an encrypted aggregated result. And then only the clients have a decryption key to decrypt it again and continue training. In that way, the risk of data leakage to the server is really minimized. And on top of that, sometimes you have concerns about memorization, so differential privacy becomes relevant, and you can add some kind of noise to the gradients before sending them to the server to make sure that no individual data points are being memorized by the models. There's like a research folder in the NVIDIA Flare repository, where we show some of our active research using the platform over the last few years, going from things like auto federated learning. So this is automatically tuning some of the hyperparameters like aggregation rates, local learning rates, using reinforcement learning. Then we have a tool to quantify data leakage by implementing a gradient inversion attack that could potentially be run on the server, but allowing you to quantify what kind of information can be recovered by the server through gradient inversion attacks. Therefore, you can make a better trade-off as to how much differential privacy should you apply before sending data out, given your local batch sizes, local number of iterations, all impact the amount of data that can be recovered. Then we also have some recent work, which was just presented at CVPR this year, on estimating the contributions of each client towards the global model performance. It's also really important for keeping fairness in mind between different clients. And then we have personalized federated learning solutions that allow you to get more models that are more tailored towards the local distributions of individual clients. And this is a growing amount of research that is being performed using NVFlare, and also a lot of the time, I think most of these works, all of these works actually are in the medical imaging sector, right? So we're making use of a lot of the MONAI components in these research works. Okay, so then I'll quickly show a demo and to show you how easy it should be to get started with MONAI Federated Learning. And therefore, I need to switch to my workstation, which is just a Linux workstation, and I'll share the screen here. Okay, great. So if you go on the MONAI tutorials, there's a link that will link you to this NVFlare repository. And there's actually some information about how we integrate into MONAI. as I say, there's this concept that you can take the MONAI bundle, run it, send it to the clients, and then run the MONAI algo to do the local training. And you can get started by just doing a pip install MONAI NVIDIA Flare, which is the kind of the glue between the MONAI and NVIDIA Flare packages. And this will install all the requirements. And then here, if I click on the examples, we do have some simulated examples using the FL simulator. That's kind of the easy way to get started. And then we have some more complex things. If you want to run federated learning in the real world, you also have to do thinking about client identity management and things like that. So we have a provisioning step that allows you to do things like generating encryption keys for homomorphic encryption and secure communication using TLS. So I will go with the simulation example for now. And basically, I just need to copy some of these commands into my terminal. So the first one, so we're using the MONAI model for spleen segmentation that's developed using the medical segmentation decathlon dataset. And we start by defining a job name here, which contains some configuration locally. And then we can download using the MONAI API here to download the spleen segmentation model. I'm not gonna download it now because it would override some of the configurations I already did locally, just to make it run a bit faster for this demo purpose. But after you download, you can basically see the structure of this folder being like this. We prepare, as part of the example, we are already provide the configurations that you need for your client and your server. And then this folder contains the MONAI bundle. In this case, also the pre-trained checkpoints, which we are not using in the example, but you could do fine tuning from these pre-trained checkpoints. And then the main file is this train.json that's used during the training. So let's have a quick look there. Oh, that's not a config. Okay. So as you can see here, this is the MONAI bundle style of defining how a training pipeline should look like. It's defining the model architecture. So here we're using a 3D UNet. Some information about the loss optimizer, training transformations, all pretty standard MONAI stuff, and then the data loaders and so on. We also have a command. Here we have a little utility script to download the dataset. And then here I'm just replacing the default path that's to my local location of that dataset. So this should not take long because I already downloaded it earlier. Okay. And then here, this is the NVIDIA Flare simulator command. So now we're telling it to use this job folder, which contains all the configuration files that I showed. And we're just defining the workspace, which is basically the output folder where all the results will be saved. If you're on a resource limited machine, you can actually do a simulation with a large number of clients, but just using maybe one thread. So in that case, your machine will basically sequentially run the training task for each of the clients. So you can use the same GPU, right? But to make it more efficient, here we use 2 threads. So now both clients will run in parallel. And then we can also define things like how should the clients be called, and on which GPU should they run. So in this case, my machine has 2 GPUs, so I use one for each client. Okay, let's start this. And you can see that both clients are kind of starting at the same time. They're running in parallel threads. I reduced the training data set here a little bit. So this is using the cache data set. So in the beginning, all the data will be loaded into memory, both training and validation. And here you can see some of the information that shows that the server is sending the global model to the clients, and then the clients do some matching with their local version of the model, right, to convert, and basically update the state dictionary to then start learning from the state of the model. Okay, so then you can also visualize the progress using TensorBoard. Move that back. And yeah, you can see that training accuracy and training loss is behaving as expected. And then also validation accuracy is going up, and mean dice is going up, and we see both clients, they are being validated on their local validation data, right? Because in this scenario, the server doesn't have any data. Okay, I also wanted to point out another example that we have as part of the simulation examples. It's a federated statistics scenario. So here we again use the MONAI bundle concept, and actually we utilize some of the MONAI core functions that are also used in the auto 3D sec functionality of MONAI, which I think you will be hearing about later. So this is a tool that can analyze the whole data set and compute some statistics. So if you go through this notebook, you can, again, this is actually also showing not just the command line usage of the simulator, but you can also use like a Pythonic style to run the simulator. And then you get different statistics of number of data sets for each client. You can plot histograms and compare intensity profiles across the different clients. Okay, with that, I think I'm right on time, so I'll stop